right. So it says determine delta G for the following reaction. This is number 3 here. And use delta G F from the Gibbs energy formation from a data of it from a table. Okay. So number 3. So I have this chemical formula here. C3H8 plus 5O2 yields 3CO2 plus 4H2O. I'm just not going to include the phases, but I know this is here is a combustion reaction, right? This here is a 5, not an S here. There we go. I know that the delta G, not a formation of C3H8 would be negative 23 kilojoules per mole. I know that delta G formation of CO2 would be negative 394 kilojoules per mole. And then finally, delta G formation of H2O would be negative 237 kilojoules per mole here. So that's gets determined for the following reaction. What are we determining? So to determine the delta G for the following reaction here. So let's do this problem, and we're gonna say that we know that delta G naught of this reaction here. You can think of this problem as kind of like Hess's law, right? Where Hess's law states that the enthalpy change of the reaction is simply the delta energy change between the products minus the delta energy change, enthalpy change for the reactants, right? So I can basically say that delta G here for the reaction will also be basically delta G, or Gibbs free energy, of our products minus delta G of our reactant. So it's very, very similar to Hess's law, but it's kind of rearranged, right? It's rearranged for delta G, for Gibbs free energy. And we know that we can actually relate this to Hess's law, because I know that delta G is simply just the enthalpy change. I can do delta H here minus temperature times delta S, right? Where delta S here is the entropy. So this formula here allows me to relate delta H with delta G here. That's why we can use this reaction here, because it's very, very similar to Hess's law. But we know that if we have a change, if our temperature here is consistent, and we make our entropy here constant, then we can basically state that delta G here equals delta H here, right? So we can basically use this this formula here to solve for our problem here. Let me keep this actually. I'll keep this for reference. I don't know why I erased it. Okay, so I'm going to let you think about this problem for just a couple seconds. So think about delta G for products, delta G for reactants here. What are my products, what are my reactants in terms of our chemical equation, and how will we solve for this problem here? So I'm just going to turn on a light because it's just a little bit dark in my room. So I'm just going to leave you this question for a couple of seconds here. So what we have here is, again, we want to know, we're determining the delta Gibbs free energy of our reaction here. So we have basically delta G of the products minus delta G of the reactants, right? So I forgot the subscripts here, which is formation here. Let me write this down here. Delta G formation here. And basically I know my products here. My products here are carbon dioxide and water, right? So I can say basically our products here are carbon dioxide, which is this guy here, number 2, and number 3 here, water, right? So let me just write down number 2 and 3 here. So very, very similar to Hess's law, where instead of enthalpy, we're just using Gibbs free energy here. So this is going to equal products here, which is 3 carbon dioxides, right? Again, I'm forming 3 carbon dioxides, so I have to use this Gibbs free energy 3 times, right? coefficients do matter here. So we have to make sure that we know that this here is already a balanced chemical equation. So we don't have to worry about the coefficients being incorrect. So we can write here 3. I'm going to multiply it by the Gibbs free energy of carbon dioxide. So this is 394 kilojoules per mole. Plus, remember, it's a sum of, this is a sum of our products, right? So you can basically say this here is a sum, and this here would also be the sum, actually. So maybe I'll write the summation here. Plus, so this is all kind of in brackets here, plus the water, right? I'm also making water as our products here, right? So I have 4 waters here, which means I'm making 4 times negative 237, right? 4 times negative 237 kilojoules per mole. So basically that's all of that here, plus, or minus, sorry. So I'm going to minus my delta GF of my reactants, right? In this case, my reactants here, I have this is my propane, and this here is my oxygen gas, right? So propane would have a delta GF of negative 23 kilojoules per mole, right? So we have here, and that's only simply just a 1, right? So we have basically 1 times, this would be negative 23 kilojoules per mole. And then for oxygen gas, because I know here it's a diatomic molecule here for oxygen gas, oxygen already exists as O2. Remember, it's a diatomic molecule. You can think back to Hofmannsthal, the mnemonic here. We know that this here, because it's just simply just an element that exists as 2, it does not have a delta G of formation, and it's actually 0 in this case here. So we can say that so we can just simplify this this equation here and say that we can say that our formula here is we can actually get rid of the oxygen here, so we don't even have to write the oxygen here. You could say plus also 0, but it doesn't really matter. Adding 0 to the equation doesn't do anything. So to get my calculator, I'm doing 3 times negative 394. Gives me negative 1,182 kilojoules per mole, plus whatever 4 times negative 237 is, which is negative 238, or sorry, negative 948. So I'm going to add both of these guys up, and then I'm going to minus that by minus 23 kilojoules per mole. And then I'm going to add, again, it's just simply just algebra right now, right? I'm going to add both of these guys up first. So negative 1,182 plus negative 948 would give me negative 2,130 kilojoules per mole. And I'm going to subtract that by 223 kilojoules per mole to get my final answer, which is negative, it's minus, so this here is plus, sorry. So this here would be negative 2,107 kilojoules per mole. And this here would be the delta G F, delta G naught of my reaction here, So this solution here is correct. Again, they wrote here, they wrote kind of the same thing as I did. They basically just wrote out Hess's law, and then they looked at the products and the reactants, and then they just simplified here. So the solution here is correct. We can, and then I'm going to say we can relate Gibbs free energy with Hess's law because delta G equals delta H minus T delta S. Therefore, Hess's law can be rewritten as a function of Gibbs free energy. Solution here is correct.